Okay, so the title of the conference included optics, kindly. Because I have a strange feeling that for many people in this audience, quantum mechanics may be a good language in which to describe optics rather than the other way around. Yeah, that's just the way things evolve, the way optics has been removed from the curriculum. Okay, so you could think of this. So I will freely move back and forth between the languages. Of course, you've had a masterly introduction to quantum mechanics in the morning. Okay, so since we're talking quantum mechanics, here's the Stern-Gerlach experiment, right? So, I mean, these particles get split into two beams by something. So the gentleman who believed in particles, this is what he said, okay? And I'm happy to go further back into the past, or almost further back into the past than Michael Berry. This is from Newton's optics. He says every ray of light has therefore two opposite sides. And incidentally, he's referring to two opposite sides of the same polarization direction. So it's a double-headed arrow. Somewhere else in the book, he says it has the symmetry of a brick. And so I would say that apart from believing in waves, he made the most remarkable contributions to wave optics. Okay? We'll be talking about polarization of light, which you've already been introduced to tersely in Kunda's lecture, and I'll start from the same point, maybe with different notation. So for at least half this talk, the electromagnetic wave direction of propagation will be fixed. It's along Z, okay? So there is this standard phase factor, and then in addition, you have an X component and a Y component of the electric field, and their amplitudes and phases can be encoded in two complex numbers, right? So R is real part, and oops, no, that's not what I meant. Yeah. So we'll really zero in on this. We'll imagine that we are sitting at t equal to 0 and z equal to 0 or something like that, and look at this A1 exponential I phi 1, which we call Z1, and so on. So these are the complex electric fields. And look, what is this? It's two harmonic oscillators. So I have to confess that I'm going to talk about these two harmonic oscillators for half the lecture. So, well, I don't see people heading for the exit, but yeah. So if you separate each of Z1 and Z2 into a real part and an imaginary part, you have a Q and a P. You can also think of those as the coordinate and momentum of each harmonic oscillator. So on the one hand, we'll use classical mechanics of these harmonic oscillators, or we will treat this psi as a two-component wave function for a two-level system. I'll be quite opportunistic, depending on whatever is convenient. And I have to confess that the system I used to set these mathematics did not have a symbol for Hermitian adjoint. So I'm using a bar, right? The same bar that you use for complex conjugate, put on top of a two-component object is the Hermitian adjoint, okay? So if you calculate the absolute value in the usual way, right? It's the sum of Q1 square, P1 square, Q2 square, P2 square, and we'll take that to be 1, right? If you're thinking quantum mechanics, you're normalizing the wave function. If you're thinking classical optics or classical oscillators, you're fixing the energy at some convenient value, okay? So, yes, I have to say that I did not change any of my transparencies after listening to both the morning talks. So you will see a fair amount of overlap. And another good reason is that I don't recall missing an opportunity to listen to a lecture either by Professor Mukunda or by Professor Berry, if it was ever possible. So any correlation you detect could well be due to that circumstance, right? So we know that if you look at the path executed by the tip of this electric vector in the transverse plane, it's an ellipse. It's a Lissajous figure, if you like. And now, to start with, we're going to not worry about, we're interested in the shape of this ellipse. So the two things we are not interested in is the size of the ellipse. So you could make it bigger or smaller, but we'll still say it's the same shape if its major axis is pointing in the same direction, if the axis ratio in the same direction. And in the notion of shape, we'll also include the sense of traversal of the ellipse. So there'll be an arrow on all the ellipses that I show you. Position in the orbit. But let's say we're interested in what opticians call the state of polarization. So you're not going to, wait for femtoseconds and catch it at a given phase. You're just interested in that shape, okay? So in the language of our two complex numbers, Z1, Z2 is the same, is equivalent to lambda Z1, lambda Z2, where lambda is another complex number, right? So the magnitude of lambda scales up the ellipse, and the phase of lambda moves your electric vector along the ellipse. And initially, so this is the ray space when you decide to ignore both of these. Okay. So if you're just counting parameters, you had 4 to start with in Z1, Z2, or Q1, P1, Q2, P2, and by throwing away 2 of them, you now have 2 parameters. So clearly, when you're talking of states of polarization of light, state being used in the sense I've just explained, you're talking of a 2-parameter family, okay? So clearly, what you're really interested in is the relative amplitude and the relative phase. So you heard this in Michael's talk, that Poincare decided that he would just divide these two, Z2 divided by Z1. So you've got rid of that lambda, so to speak, and you now got a complex plane, and therefore it would seem that it's logical to map these states of polarization onto a complex plane. But I've been scooped by Poincare on this, right? This ratio Z is fine, except for one case, okay? If Z2 happens, let me see, did I get it right? Yeah, if Z1 happens to be 0, well, depending on how it approaches 0, Z approaches infinity in a different direction. So you might think that these different directions at infinity in the complex plane all represent different states of polarization of light. But ultimately, if Z1 is 0, then its phase is no longer relevant, right? And you have something polarized along the y-axis. So really, all these points of infinity have to be gathered together in a single point. So I don't have some convenient sheet of cloth or paper. We just gather them up and put them on top. And that is what is achieved by the stereographic projection. So this is what you heard. So I've just, on the right side, you have this convenient representation of the stereographic projection. The sphere sits on the plane, and you sit at the North Pole, and you look at any point on the plane, and map it onto the sphere by putting that line. And of course, all the points at infinity end up on the top. So that has achieved the goal of throwing away the irrelevant phase of Z2. So what you have on the left side is just where the various points go. Infinity goes to the top, 0 sits at the bottom, and you can see where -1, I go. Now at this point, I'm going to, just for convenience, I'm now actually going to, this may be a bit abstract, so I'm now going to show you a picture of all these polarization states, but I'm going to change convention a little bit. This is something which, people in quantum mechanics wouldn't mind, right? With your permission, I'm making a unitary transformation from Z1, Z2 to some ZR, ZL. But even in optics, these have a nice interpretation. ZR describes right circular light and ZL describes left circular light. So you can see that most easily by putting Z2 equal to I times Z1. So then ZL disappears, right? I into I gives you a minus sign, whereas ZR doesn't disappear, right? And Z2 being I times Z1 is simply saying that the oscillator along the y-axis lags the oscillator along the x-axis by 90 degrees in phase, okay? So actually one interesting experiment which I have not carried out is to make a set of cards with all these polarization ellipses drawn on them, and then give it to a kid in any standard, say 3rd, 4th, 5th, 6th, and ask the child to arrange them in such a way that, similar looking things are nearby. That's the spirit of topology, right? So that's exactly what I've done here, yeah? So, So here are, and please note the arrow is double-headed because this represents the entire oscillation of the electric field, right? So notice also that, so clearly, I've omitted a whole lot in between, but clearly there's continuity going from here to here to here to here to here. So these are all the linear states, which now with the new definition of the Poincare sphere, ZR divided by ZL rather than Z1 divided by Z2, or the other way around, Z2 dy. With the new definition, you can see that in one case, right circular goes to the top. I mean, that was already mentioned. And left circular goes to the bottom. And then going from any linear state to a circular state, you go through elliptic states. Again, right ellipse, left ellipse. So I think even without any complex analysis, just looking at these pictures would convince any reasonable person that these states of polarization should be placed on a sphere. So this is like a map of the Earth where it looks as if, you have many north poles at different longitudes, but all at the same latitude of 90, but actually they're all the same point, okay? So that's just, now, there is another route to the sphere which was mentioned, and this was taken by Stokes. I tried very hard to get rid of these two inverted question marks, but I could not. So, so what did Stokes do? He indulged in, to use a phrase I learned from Professor Mukunda's lectures, he indulged in anticipatory plagiarism, okay? So in this case, he said, okay, here's a wave function. Let's construct the pure state density matrix by multiplying psi with psi bar, right? And so you get these 4 quantities. And then let's expand that in terms of the Pauli matrices. That's exactly what Stokes did. Now, I'm not being facetious when I say that he anticipated von Neumann and others, because, I mean, one of the bonuses of giving this talk is I really went back and read some original papers. So this is the quote from Stokes. Let's look at it. So he is really interested in a statistical ensemble of polarized beams. And he wants to know what characteristics of that ensemble are measurable. And he concludes that you need 4 numbers, right? So I couldn't get hold of the von Neumann paper, but I wouldn't be surprised if his reasoning is somewhat similar, though more mathematical. Yeah, I was also going to say that for, like Professor Mukunda, I will be pure from now on. I mean, not mixed, yeah? By the way, I did not find explicitly any sphere or in his paper, but okay. For future reference, incidentally, I, Q, U, and V are not only of interest to a theoretician because you expand a density matrix in terms of Pauli matrices, but also of interest to an experimenter. So for example, Q is what you would get if you looked at the difference of intensity between a vertical and horizontal Polaroid. And there are similar nice experiments for U and V, okay? So they're very much tied to observation, and you've got rid of this arbitrary phase of the wave function, so, right? So this is really the density matrix or ray space. For future reference, I'd also like to write this out. Looks a bit gory, but it's the same thing. Like Z1 bar is nothing but Q1 square plus P1 square, and so on, right? So I've written it out, and we'll come back to it. But specifically for pure density matrices, there's the famous identity which says that rho squared is equal to rho. And translated into this, the identity is that is the one that I've written down here, right? Yeah. So we'll leave it at that, because there's another piece of anticipatory plagiarism here, which I will come to. Okay. Now, the interference of polarized light was studied by Fresnel and Arago very soon after the experiments on the interference of light. And they noted many things. In fact, there are some 4 laws which are attributed to them. Stokes discusses it extensively, okay? But in this language, the way we would think about the interference of polarized light is you have 2 beams, psi 1, psi 2. You calculate the total intensity of those 2 beams and see how it varies as you play around with the phases of these beams, right? Much easier to do than actually setting it up in the lab, right? So you have the bar, which means Hermitian adjoint of psi 1 plus psi 2, multiplying that. So you get individual intensities added up, which you would get even for bullets or something like that. And then you have the interference terms, right? Of course, the intensity is real, so the interference term has two complex conjugate rings. So it's natural to ask, when will the interference be constructive? When will this term be a maximum? So you will notice that the real parts add and the imaginary parts cancel, right? Because they come with opposite signs in these two terms. So if you can get rid of the imaginary part and the real part is positive, as you heard in the morning, that's when you get constructive interference. And I don't think any of this was new to anyone for hundreds of years, perhaps. Yeah. Now, one might wonder whether one has access to the imaginary part. One does, because you just have to shift one of the beams by putting in some piece of glass in phase by pi by 2, and then imagine sticking an eye onto, say, psi 2. So the first term would develop an I, and the second one would develop a minus I. So now you would pick up the imaginary part of the original psi 1 bar psi 2, right? So that's the interference term. Now, another way of thinking about it, that you could divide the psi 2 beam into two pieces. One, you project it onto psi 1. I mean, in the case of linear polarization, literally means stick a Polaroid pointing along psi 1. But people who do quantum mechanics have a more sophisticated understanding of projection, right? So you're really hitting psi 2 with this density matrix. That's what you're doing, right? So you have psi 2, you've projected on psi 1, and then you get some version of psi 1, whose phase is the phase of this object. Of course, the amplitude of this object clearly tells you that if psi 2 is not the same as psi 1, the two won't be of equal intensity, but that doesn't matter. And you can again see that if the phase, if this is real and positive, you're going to get constructive interference. So this is the form in which we could use it. Okay? So now, you've all heard the name of Pancharatnam. I believe this paper, according to Google Scholar, has some 1,677 citations, something like that. But it doesn't necessarily prove that 1,677 people actually read the paper. Interestingly, that paper is written in a very classical style. And right? So whatever I just told you, this is the way that he states it, and no harm in reading it out. Right? We will be guilty of no internal inconsistency if we make the following statement by way of a definition. The phase advance of one polarized beam over another, not necessarily in the same state of polarization, is the amount by which its phase must be retarded relative to the second, in order that the intensity resulting from their mutual interference may be a maximum. I mean, the other sentence carries on. So this is the beginning of his paper. He gives this definition, which is pretty similar to what we said at the bottom of the previous slide. Right? As I said, nothing earth-shaking so far. But the definition. So this is, now I have fast-forwarded to section 5 of the paper. And from section 1 to section 5, I'll tell you what you do not find in that section. You do not find any mention of complex electromagnetic fields or phases. It's entirely in the ray space, entirely in the Poincare sphere, which is why Michael, in his article in Current Science, described him as a virtuoso of the Poincare sphere. So I will not try to reproduce his argument, okay? But what is interesting is that it is carried out entirely in the ray space, which is the harder part, right? Because as you heard from Mukunda, I mean, given a chance, one lifts to the Hilbert space and works there. But so let's look at this statement. When a beam of polarization C, so C is some point on the Poincare sphere, is decomposed into two beams in the states of polarization A and B. Now it's implicit here that because it's been decomposed in this way, A and B are automatically in phase with C. But then you find that the phase difference between these beams is given by something, okay? Now this something happens to be the solid angle. And the reference for that, so there's a very complicated formula for tan of this E prime or something. And then he finds an 1897 book on spherical trigonometry. Okay? So he says, this clearly tells us that we have this unexpected geometrical result. So the word geometrical occurs here. Now, in preparing the lecture, I could have taken a bet for any sum of money that we would hear about the Bargmann invariant in Professor Mukunda's lecture. So here it is, right? I mean, maybe I'm indulging in a little anachronism, but this statement, the earlier statement about C, A, and B can be translated. I mean, it happens to be the case where, two of the phases are 0, and therefore the third one is not 0, right? So, but what is interesting is that, I mean, as I said, Pancharatnam did not have these complex amplitudes in his paper. But if you write it in this way, you might wonder, does it depend? And you notice the nice cancellation property that it has as many, every psi occurs as a psi and a psi bar. So if you put an e to the I alpha here, you get an e to the minus I alpha there, right? Okay, so that's, and I won't dwell on this because you've heard quite a bit about it. What I will probably do is give you a very elementary example, okay, where you can intuitively see that this has to happen. So this is a Poincare sphere where C is circularly polarized and A and B are on the equator of the sphere. They are separated by 90 degrees on the Poincare sphere, but they are actually separated by 45 degrees in real space, okay? Because notice, by the time this guy turned by 180 degrees, we were back to where we started, right? So this doubling of the angles is very characteristic of mapping polarization states onto the Poincare sphere. So here is the psi corresponding to the circular polarization. I think I've switched back to x and y here, right? So you have Ex and Ey lagging in phase by 90 degrees. And this you have only Ex. And here you have Ex and Ey in phase, right? I have not even normalized them because anyway we are going to do the phase, right? So in this case, without much effort, the inner product of these two will be 1, and of these two will be 1 plus I, and these two will be real. So this is real, but this is imaginary. So the phase you get is 90 degrees, and anyone who has cut an orange knows that this is 1/8 of a sphere, so pi by 2 again. So this is just an example, and actually Pancharatnam seems to show a certain mathematical bent, even though his papers are full of words, like saying we will not be guilty of any inconsistency or something like that. So here he also points out that this definition of phase has the nice property that a beam is in phase with itself. If a beam is in phase with the second beam, then the second beam is in phase with the first beam, but it's not transitive. If we reinterpret in phase of in terms of, when you say two people are on the same page, I think this applies equally to, usually most people are on the same page with themselves unless they're very inconsistent, and hopefully unless there's a major misunderstanding, if A thinks he's in phase with B, then B thinks he's in phase with A, but we all know that that doesn't carry further, okay? Okay, so I'm taking a small break to go into some of the historical aspects. A small declaration of conflict of interest is that I have served these two journals at different times on their editorial board, but in any case, these are the issues of current science and resonance on which you can learn more about Pancharatnam. But I also want to make the point that he didn't just walk into the Raman Research Institute and start working on the Poincare sphere. His stern supervisor, C.V. Raman, told him that there are some very interesting interference figures in amethystine quartz. You can still see those sheets of amethystine quartz in the museum of the Raman Research Institute. And interference figures, you already saw some in Michael's talk. You put something between cross polaroids and you see what's happening, right? So here is a figure which is quite remarkable, right? It's a spiral. So just think, this is an interference fringe, which should be a location of a constant phase difference between two polarizations, two beams in different states of polarization. This is as a function of direction, okay? So clearly there was something. I won't go further unless someone asks me as to how the geometric phase helps you to understand this, right? Now, in the same spirit of full disclosure, as it's called, at the end of every paper in Nature, the author has to declare all his connections. So now I'm going to declare all my connections with the Raman Institute and polarized light and so on. So look at this carefully, okay? So the notation is that G is graduate student, N is nephew, S is son, C is collaborator, and E is employee, okay? So you can see Pancharatnam there. I only caught a glimpse of him once. I had never met him. But this is my thesis supervisor, whose name was mentioned in the morning, who insisted that I go and investigate the connection against what I thought was my better judgment, okay, until I did some calculations, okay. And a very distinguished student of Professor Raman was G.N. Ramchandran, no relation, okay. And they collaborated on this review article on crystal optics, which was written at the same time that Pancharatnam was writing his papers. It mentions those results, but that's it, right? Just as one more result in passing, okay? I also collaborated on polarized image reconstruction in astronomy with, a fellow graduate student of Ram Station, Ramesh Narayan, who is now astronomer in Harvard, so we collaborated. This is not just being employed. He used to keep asking me searching questions about polarization. And here are two people with the same name, S. Chandrasekhar, who really introduced me to polarization optics, because he was doing some beautiful things with the optics of liquid crystals. And this is the other Chandrasekhar who was mentioned this morning in Chicago, who sort of revived the sleeping beauty of the Stokes parameters in his book on radiative transfer. And he relates in the preface how he wanted to solve this problem of radiation being scattered in an atmosphere. And he was looking for the appropriate mathematical tool, and he found it, okay? And as part of this break, this is not the Raman Institute, but this is where I was exported to from the Raman Institute. It happens to be a sister institute of ICTS, so I thought I can show it in that connection. National Center for Radio Astrophysics. And I thought I was bidding goodbye to geometric physics, but not so. So let me tell you what's happening here. There are 30 radio telescopes, but this picture fortuitously shows you 3 of them. Now, as every radio astronomer knows, every radio telescope generates a signal, which is a vector in a Hilbert space, right? It is a complex string of complex numbers. And you take 2 of these and you form their inner product. We call it the correlation of the 2 signals, okay? Which is the interference term, really. And maybe Professor Berry can check in his timeline, a radio astronomer by the name of Graham Smith at Cambridge, I think, actually suggested that when you have 3 radio telescopes, you should take these 3 correlations and multiply them. And the radio astronomers call it closure phase. So that's the Bachmann invariant, if you like. So there was a young man called Sanjay Bhatnagar there who was writing the last chapter of his thesis, and he was looking at correlations. Of course, the sources are mostly unpolarized, but the signals come from a given polarization of a given antenna, okay? Now, it's humanly impossible to make 3 dipoles or any other more complicated object which will respond exactly to the same polarization, okay? Wow, great. I'll tell him. I'm in regular touch with him, in fact. Sanjay was wrestling with this fact that, by the way, this closure phase vanishes for a point source, right? But it wasn't vanishing, and he attributed it to the fact that the 3 polarizations were not identical, right? So we sat down, and no prizes for guessing what this spurious closure phase was. It was the solid angle made by the 3 points of the Poincare sphere of the 3 feed. Actually, radio astronomers have this strange thing of calling this thing the feed, because from radar, it kind of feeds the signal to the sky. But of course, it's more like a mouth, it receives, okay? So anyway, that's a small digression just to tell you that, geometric phase followed me to NCRA, okay? Okay, now, Mukunda mentioned in his lecture that I might not mention some of the early things I did, and there's a good reason for it. I have to be rather ashamed of missing something, okay? So sometime, soon after joining RRI, I knew about the Poincare sphere, and Radhakrishnan had already done some of the pioneering work in interfering polarized, looking at polarized sources with interferometers and so on. And I said, okay, you have two antennas of different polarization, and then you say their phase difference is so much. What is it? Now that's interesting, right? He's the first cousin of Pancharatnam and knew him very well. And my thesis supervisor is Pancharatnam's brother, but neither of us brought up this convention for the phase difference. I said, okay, so let's do any phase difference, right? We've got all these points on the Poincare sphere. Is there some way of synchronizing all of them? Can we put a dot on each one of those pictures? I mean, that's a very pictorial way of looking at it, right? So we look at the picture a bit later, but right now, this normalization condition puts you on the three-sphere, S3, right? You already saw that. The sum of these four things, Q1, P1, Q2, P2, squared, adds up to some constant, okay? Now, what happens to these Qs and Ps if you keep shifting the phase? So that's exactly what happens to two harmonic oscillators of the same frequency, right? It moves around that orbit, okay? So you have this S3, you can take any point on S3, and then if you look at it, either one possibility is to just let some time elapse, or you could shift its phase by some other method, and it would move along a circle, right? So clearly this S3 is filled with circles, I mean, topologically circles, because it comes back, right? Harmonic oscillators, two harmonic oscillators of the same frequency will return to the same Q1, Q2 value, right? Same point in phase space. Now what we already know is that if you didn't worry about this phase, if you just collapsed all these circles to a point, you would have an S2, right? The Poincare sphere. So, natural question to ask is, so here is this S3, it's got all these circles in it, yeah? And I want a phase convention, so I should put one dot on all these circles. So in other words, I should draw a surface inside the S3 which cuts all these orbits at some point, which arbitrarily, I didn't know about the Pancharatnam convention, this is why I have to be ashamed of that, right? And see whether that's possible. So I did it by trial and error. So let's start with right circular. And I mean, there are lots of them here, but it's really only one. By the way, even this row is identical to this row, right? I mean, just for duplication to attach this to this. So this is the same as the earlier picture, but now there is a dot. So there's just a single right circular phase. And now we're going to move down the Poincare sphere all the way down to left circular, right? By making this elliptic, then linear, then elliptic in the opposite sense, and then circular in the opposite sense. And we will assign between any two of these the phase by Pancharatnam's convention. Now, the right way to do it would be to write down these complex amplitudes and check that the phase of that scalar product is 0. But in this case, I'm doing it more intuitively from the criterion that, so in this case, for example, it would make complete sense if you want this to constructively interfere with this, right? Forget the perpendicular component, right? You would want this to reach here and want this to reach here, okay, at the same time. And of course, the perpendicular components would also be in phase. So by the time you come to linear, this one is in phase with this, and that's how you end up here, all right? And of course, exactly the same thing is happening here because this is really the same as this, okay? But now let's see what's happening here. So we are now going through linear again and through ellipses, but now the major axis of the ellipse is horizontal, right? So this is fine. So I think with a little imagination, you can believe that as this ellipse flips through linear, I mean, one way to do it would be to just look at it. Anyway, so now you find that actually this comes to the opposite side. So this is an example of a failed phase convention, right? You tried to make everything in phase. And of course, if I had read Pancharatnam's paper, I would have realized that you can't make the orthogonal state in phase with this. But, so here, so you notice that by the time you come to the bottom, you're encountering this phase discrepancy of 2 pi, okay? And of course, with our current knowledge, what we would do is we would draw a tiny loop around the South Pole and look at the area above it, which is 4 pi, and divide it by 2, which is 2 pi, okay? So anyway, this is just to give you some intuition, but that still leaves open this interesting question of how do all these circles sit inside S3 in such a way that it's impossible to draw a surface which cuts each one of them in one point, okay? I mean, thinking of it geometrically, so to speak. Again, this is something I learned after writing that paper, very soon after. This was written in 79, and that was the Einstein centenary, so we had all these relativists visiting the Raman Institute. And naturally, I was excited about this, so I showed it to one of them, and I think Martin Walker of Cambridge told me, yeah, these are the Clifford parallels. I said, okay, so let's go and find out what are the Clifford parallels. So Clifford is this brilliant mathematician, geometer, right? And he had done this, right? For his own very interesting reasons, I also took the opportunity to read Clifford, but I will not quote him to you. He is certainly more difficult to read than Stokes, right? And many of his motivations are algebraic. I mean, some of you may have heard of Clifford algebras. And in fact, he constructed this whole object, geometric object, using, he called it elliptic space, I think. So in any case, so I'm going to actually try and show you the three-sphere with all these circles inside it, arranged in such a way that it becomes very difficult to, in fact, impossible to cut all of them with a spherical surface, okay? That's going to take a while, so let's prepare for it. So how do I represent it? Of course, the slide is two-dimensional, but I think if I draw some three-dimensional figure on it, pretty much with a little either skill or luck on my part, I may be able to convey a three-dimensional figure. And this S3 is intrinsically three-dimensional, right? We get a hint from how people have represented the globe on a flat atlas. So one way of representing the globe would be to have one disk for the northern hemisphere and one disk for the southern hemisphere, right? Then attach the two disks at the equator. And that's exactly what we're going to do, okay? And the claim is that, as I said, each circle corresponds to a given state of polarization. So it'll be a circle. They have to be non-intersecting, because remember, these are phase trajectories of some simple dynamical system. So if two of them intersect, then after that they're doomed. They have to follow the same Q and P, so they don't intersect. They're linked, as it turns out. Any two circles of them are linked to each other. And he called them parallels because they have a constant separation. And this separation, I think, turns out to be something like the separation along the geodesic. Of course, if I have two circles, what do I mean by their separation? So the logical definition was go to any point on one circle, find the nearest point on the other circle, and nearest is with respect to distance in this four-dimensional space of Q1, P1, Q2, P2. And that you call the separation between these two. And then if that separation doesn't change as you move along the curve, you call them parallels, okay? So incidentally, each line of latitude of the Poincare sphere, so every point is a circle. And if you take, for example, one line of latitude of the Poincare sphere would be all the linear polarizations, right? So if you take that, then that's a torus. But curiously, it's a torus living in 4 dimensions, and it's actually, in a geometrical sense, it's flat, which is kind of interesting. Now what the failure of this phase convention tells you is that we are dealing with an interesting kind of geometrical object, examples of which had been found earlier, but the general theory was kind of put in place by mathematicians in the 1930s. So let me say a little bit about that theory. If you take the Cartesian plane, by the way, for the first time, I live in a place where the scientists are outnumbered, the School of Arts and Sciences. So if you walk into our school and if you want to tell whether a person is, belongs to science or to the, you simply have to ask them, do you think Descartes was a great man? And they will say yes. All of them will say yes. Then if you ask the scientist why, he'll say because he gave us X and Y. And the other people will say because he gave us mind and body or something like that. Okay? But in any case, the point is that on this plane, you take a point, you can assign it an X coordinate, you can assign it a Y coordinate. And that's why this is called the Cartesian product of two lines. It's equally true of a cylinder. Of course, one of the coordinates will be an angle, which will be periodic, but quite apart from that, it's still the Cartesian product of a circle and a straight line. And the classic example of something where this Cartesian product fails is the Mobius band. So here it is. You can draw a kind of center line, if you like, and say, okay, that is height equal to 0, and every point has some height in the direction of this arrow, and you want to do it continuously, but by the time you come around, this thing has turned upside down, okay? So this kind of situation gave rise to the concept of a fiber bundle, which was mentioned briefly in Mukunda's talk. What I did not know, which I learned from Michael, is that people who talk about this subject are said to suffer from a disease called bundle fibrosis, okay? But anyway. So the idea of a fiber bundle is that you have these fibers. This is going to be a somewhat informal definition, right? And each of these fibers, in some sense, belongs to some point in some space, which is called the base space. So, for example, you had the ray space, and then when you put the Hilbert space or the space of complex vectors on top of it, a whole bunch of complex vectors projected onto the same point in ray space, right? So so in this case, we had this circle, the black circle, and this is a bundle, if you like. And these are the fibers above it. And this happens to be twisted because you are not able to assign, it's not a Cartesian product. If it were, you would be able to assign a height coordinate and an angle coordinate to any point in a continuous way. And you're not able to do that. And clearly one has to, if the failure to find a phase convention on the Poincare sphere was not just due to my lack of skill, but due to something intrinsic, then clearly one should look for fiber bundles. So it so happens that the geometric object, the same geometric object which Clifford wrote down, was one of the early examples of fiber bundle, and it's known as the Hopf fibration, okay? And not all of them are twisted, by the way, huh? I should say that. So you can have fiber bundles which are not twisted, but it's still convenient to think of it that way. Okay, so here is Hopf, and you don't have to know German, and you don't have to know what happened in the previous 4 sections. A lot of things happened in the previous 4 sections of the paper. I just want you to note the resemblance between these equations. So if you replace x1, x2 by q1, p1, I mean x1, by q1, p1, and x3, x4 by q2, p2, and xi2, xi3, xi1 by qu and v, then this last equation will tell you, this one, tells you that the sum of the squares of these 3 Stokes parameters is the sum of these 4, the oscillator, momenta, and coordinates, whole thing squared, okay? And of course, his whole point is that this is a map. I mean, if you read basic German, it'll tell you that you're going from the 3-dimensional sphere with radius r, tells you, these people are thorough, so it tells you where its origin is, where it lives, all that, onto the 2-dimensional thing with the radius r squared, etc., etc. And as in German, they keep you in suspense, the verb comes at the end. It's mapped. So this is the Hopf map from the 3-dimensional sphere living in 4-dimensional Euclidean space to the 2-dimensional sphere living in 3-dimensional Euclidean space, right? And that is the other piece of anticipatory plagiarism which you see when you look at the Stokes parameters. Okay, so this is just, Oh, center of the center of the sphere. Als Mittelpunkt, yeah. Null, okay, yeah. Nullpunkt is the origin of R4. Mittelpunkt is the center. And Somit is consequently. Well, Abbildung is mapping. Incidentally, the footnote 12 is also very interesting. He says that this is the only section in which we will specialize on the two-dimensional manifold being a sphere. The rest of the paper is completely general. Okay. So I said one of the fun parts of preparing this talk was to read some of these fabulous originals. Okay. So I'm going to, so I've shown you Q1, P1 as a kind of horizontal plane, pointing towards you, and Q2 as the vertical one. And you're supposed to infer the value of P2 from the fact that the sum of all the squares is 1, okay? So here it is. Yeah. P2 is, this is the southern hemisphere, right? So P2 is minus the square root of this. And here P2 is plus the square root of this. I'm showing you these circles, but I'm breaking you the news bit by bit, okay? Not giving you the whole thing in one shot. So if you look at this one, this is the oscillator in which Q1 and P1 circle around in the way that they normally do, right? So when Q1 is maximum, then goes past it, right? P1 becomes negative. Now the other, of course, there's no fundamental difference between the X oscillator and the Y oscillator, but the way we are representing it, they're going to look very different, right? So if you look at the Y oscillator, right? So in the southern hemisphere, this is what happens, right? P2 is negative, so Q2 decreases, yeah? The corresponding coordinate decreases when the momentum is negative. But then the equator, where P2 is 0, is this surface and also this surface. So these two are supposed to be glued together on this surface, exactly as you could glue maps of the northern and southern hemisphere together, right? So this is a circle, but I would like you to believe that this is also a circle, right? This goes down, reappears here, goes up here, into this hemisphere comes. And you can see these two circles are linked, okay? Interestingly, these are the circles with the maximum separation, okay? Two orthogonal states. Okay, so now what I've done is, see earlier we put all the energy either into the X oscillator or into the Y oscillator. Now I've given them both some energy. So clearly now the amplitude of the X, the maximum value of Q1 is not going to be 1, right? It's going to be less, right? So Q1 circulates like this, as it did, and Q2 also does exactly what we said, but we are now looking at the combined motion, okay? Right? So in the southern hemisphere, right, Q2 is decreasing, and then, so there's the cylinder, but the cylinder is just to help you to visualize things. The actual trajectory is in black, goes down, reappears on the other side, goes behind, comes back and joins. So it's a circle lying partly in the northern hemisphere and partly in the southern hemisphere. And you can check that it's linked to all the other circles we've talked about, okay? So basically, I'm trying to interpolate between these two extreme cases of all the energy in X and all the energy in Y. But before we do that, we should note that even with this distribution of energy between the two oscillators, say equal amount, there's another possibility, right? When Q1 is at its maximum, the other one need not be at its maximum, right? So I've just made one more sketch, okay? So same situation, distribution of energy, but now it just so happens that when Q1 is at its maximum, Q2 is at, in fact, in this case, both happen to be at their maximum, right? Okay, so this goes here, reappears here, and goes back. But it's a circle, that's the important point, it's a closed curve. Okay. So now all I have to do is to combine all these figures, all right? And that was beyond my powers of drawing. And the other thing one can do is, if one wants to economize on these spheres, what one can do is represent this three-dimensional sphere, again by stereographic projection, the same trick works, in a three-dimensional Euclidean space, okay? So the next figure is going to be all these Clifford parallels in their full glory, but now showing you only one three-dimensional space, and of course leaving out the point at infinity, right? The point at infinity is the point of infinity. As I said, it was beyond my powers to draw it, but I fortunately found a more illustrious illustrator, right? So here it is. So you can see these tori, they're topologically tori, made up of these circles, and this is what it looks like. So I just thought I'd leave you with a more pictorial and intuitive introduction to the Poincare sphere and what happens when you add phase back to the Poincare sphere. You get this three-dimensional object, which happens to be the Hopf fibration, whose seeds were sown long before in the mathematical or physics literature. Okay. You heard again in Michael's talk, there is one more geometric phase associated with polarized light, and same history that he mentioned. If you have a medium in which the refractive index depends on position, then light can curve, okay? And if you're clever enough, you can even make it describe a space curve, right? Not a curve which can be pressed into a plane. And this was the problem which Bertolotti took up. And the fiber, of course, required more technology, right? So maybe just one more word about the papers by Rytov and Vladimirsky. So actually, when these experiments came out on coiled light, I think that's the nice phrase which Michael coined for these things. I said, look, I've seen this before, the fact that if light traverses a space curve, its linear polarization goes around. So I went to volume 8 of Landau and Lifshitz, and there, of course, they refer to Rytov, okay? Except, and I think those who are familiar with these authors will realize, they've probably chosen the absolutely laziest way of deriving this result. What they simply say is, you take a space curve and take 3 adjacent points on it, and I mean, unless it's straight, they will lie in a plane, which you call the points get close enough, you call it the osculating plane. If you take 2 points, you get the tangent vector. If you take 3 points, you get the osculating plane. And since the deviation, I think I quote verbatim, of a curve from its osculating plane is only third order, we will assume that the linear polarization, which is perpendicular to this plane, remains perpendicular to this plane. Then, of course, you've gone some distance and you have a new osculating plane, but the linear polarization remains the same, okay? So therefore, their point is that with respect to this plane, osculating plane, the linear polarization rotates in the opposite sense by an amount which is related to the twist of this osculating plane, okay? What's called the torsion of the space curve, and that's it, that's all they say. They're not really doing justice to Rytov, actually. So then I went and read Rytov's paper, and he does an honest thing. He actually solves the wave equation in a WKB approximation, and at some point he relates it to the torsion and abandons it. And as you heard from Michael, it required Vladimirsky, and I really wonder, if you're in Moscow in 1941, would you be thinking about what happens to polarization of light, or would you be worrying about the German forces? Actually, the entire university moved to Kazan or something like that, so I have to check on the detailed history. They've written a very nice paper, reinterpreting Rytov in terms of parallel displacement, okay? So I think you saw a better figure in Michael's talk. So there's one turn of a helix. So as far as the tangent vector to this curve is concerned, it's come back to the same point. And if you just look at the space of tangent vectors, that is this sphere which you have here, right? Except I've had to look at it from the top. So A is, okay, this is supposed to be further away from you, it's coming closer to you, goes around and goes away from you again. Huh? So maybe something like that. So initially the tangent vector is like this, right? And I hope I've got it right. It goes up front from A to B, then to C, and then to D, and back. E is the same as A, okay? And the polarization lives in the tangent plane. So, by the way, one of the bundles is precisely the collection of these tangent planes sitting on every point of the sphere. It's called the tangent bundle. And so if you go from one point to a neighboring point, you have a perfectly good rule for how vectors in this tangent plane, so in the context of optics, polarization vectors, how they are to be transferred from one tangent plane to another. But this rule has the property of anholonomy, which you learnt about. I think there's some famous mathematician is supposed to have had inscribed, I change, but I remain the same. I mean, that could be the motto of group theory, right? You try to do some transformation, but you find you're back there. But the motto of this subject is the opposite. You try to remain the same, but then you find you've changed, okay? In any case, so in other words, I mean, again, to use some of the language you've already heard in a familiar context, this tangent bundle has a connection, which is some sort of natural way of going from members of the fiber, that is tangent vectors, at one point to tangent vectors at a neighboring point, okay? And that's called a connection. So, in some sense, what you saw earlier on the Poincare sphere was also a connection. Given a phase of some state of polarization at one point on the Poincare sphere, there's a natural definition at a neighboring point. Of course, Pancharatnam went much further. He gave you a definition all over the sphere except at the opposite point, but at a neighboring point. So that's the notion of a connection on this fiber bundle. Some natural way of moving from one fiber to a corresponding point on a neighboring fiber. I think if some of you have seen areca nut plantations, right? They are more or less fiber bundles. You have the ground and you have these slender things, and then people climb up, and then they jump from, because they don't want to climb down and climb back up to pick these areca nuts. So they kind of shake it and then they jump. So that would be an example of a connection, okay? But this connection has holonomy, and it's a much older connection, right? In fact, if one were writing thrillers, one could write one called the Pancharatnam Connection, another one called the Christoffel Connection, and so on. But anyway. Okay, so therefore, it's quite natural that people took up the problem of combining these two geometric phases. Rajan Bhandari, whose name you've heard a couple of times, and who set up many experiments after the early work in '88 with Samuel, got interested in this topic. Okay. He wrote, many others wrote on this subject. Now, so I'd like to now talk about this problem, right? So we're going to look at the space of all directions of propagation, so no longer just along Z, but also for each direction, all possible polarizations. So this is, well, it's a fiber bundle of some kind, right? You've got S2 worth of polarization sitting at every point of an S2 worth of directions. Now, one interesting approach to this, which was taken by many people, but I think most perfectly by John Hannay, is to say, look, now that you're allowing things to go in all directions, it's still true that every orbit is going to be an ellipse, perpendicular to the direction of propagation. But since you're looking at all directions of propagation, you should now look at these ellipses with all possible orientations. For a given plane, you will have the usual Poincare sphere, and then, so why not just look at the states of a three-dimensional harmonic oscillator, right? That would be the logical thing to do. So you look at all these polarization states for light beams going every which way, right? So now we have three complex amplitudes, Z1, Z2, Z3. and the quantum mechanical analog is a three-level system. Right? And we make the same definition that Z1, Z2, Z3 is the same for our purposes as the same Z1, Z2, Z3 multiplied by some non-zero complex number. Okay? So this is what mathematicians call a projective space. So I should have, maybe I had CP1 in the title of the Poincare sphere, but I didn't explain it. It's complex projective space in one dimension. By the way, if you walk into ICTS and, well, I don't know about ICTS, but in many, certainly in TIFR, the way to tell the physicists from the mathematicians is, you ask a physicist, what's the dimension of a sphere? He'll say 2. If you ask the mathematician, he'll say 1. Because of course, they think complex. I mean, if you push them hard enough, they might do a few real things with you, but otherwise they think complex. So CP1 refers to one complex dimension, right? And in fact, we got it by a single complex variable on the plane by stereographic projection. But now we are in CP2. The same logic tells you that you started with 6 parameters in Z1, Z2, Z3, and now you are left with, if you remove this lambda, so to speak, you are left with 4 real parameters. So this is a 4-dimensional space. The good news is I'm not going to draw some pictures of what this space is like, slicing it up in different ways. Okay? Now, the first impulse is to do the same trick. We are only interested in the amplitude ratios and phase differences of these 3 oscillators. Okay? So divide by Z1. So you get 1, Z2 by Z1, and Z3 by Z1. So at this point, you may say, okay, the space of all these 3-dimensional oscillators, so to speak, or polarization vectors for beams going in all directions, will be 2 Riemann spheres, one for Z2 by Z1 and one for Z3 by Z1. Unfortunately, this does not work. I'd like to make a general remark about topology at this point. I mean, you already saw this. We had to give up the complex plane because it went wrong just at a single point. Now, in some ways, topology is a very forgiving subject. You can change angles, you can change lengths. But if you get even one point wrong, then you have not got the correct space. Okay? So in this case, there is a problem. Okay? If you look at this, you will realize that if Z1 becomes 0, right? You have these 2 complex numbers. But let's say one of those also becomes 0. Then you are left with an unnecessary phase of the other one, right? I mean, so even the 2 Riemann spheres for this is not correct. You can check that this trick does not work. So you have to do something more interesting. And of course, that's been done. And since it's a 3-level system, I'm going to tell you 3 ways to do it. Okay? So the first one I learned from Samuel. The second I learned from John Hannay's paper. And the third I learned from my collaborator, S. Sridhar. So let me go over them. If you just form a quadratic equation with Z1, Z2, Z3 as coefficients and look at its 2 roots, right? Now these roots are not going to change if you multiply Z1, Z2, Z3 by lambda. So they are just right for characterizing these 3 complex numbers. And on the other hand, if you change the ratio between any of them, the roots will change. Okay? The only thing is some of them might go to infinity because, you know, the quadratic equation formula has things in its denominator. Right? So what you actually have to do is to construct Riemann spheres for each of the roots. But there is an important difference between the earlier failed attempt and this attempt. Namely, that these 2 roots, there's no ordering between them. They come as a pair. You can't say this is root number 1 and that is root number 2. Okay? So it's an unordered pair of complex numbers. So you can either think of it as a sphere with 2 dots on it, right? And no distinction between the 2 dots. That pair of dots corresponds to a single point in CP2. Or if you like, you can, you know. So it's an unordered pair of Riemann spheres. I mean, that's the difference, okay? The other way, the second way is if you think, after all, it's a 3-level system. So why not map it onto a spin-1 system? And you can make a spin-1 system from 2 spin-half systems, except you have to throw away the antisymmetric part, which is a singlet, okay? So how do you do that? So take your favorite Poincare sphere, put 2 dots on it, theta 1, phi 1, theta 2, phi 2, construct the 2-component wave function, I could say spinner if you like, corresponding to each of these points, and symmetrize them, okay? So in this way of doing things, you have naturally generated a state of a spin-1 object. This is Majorana's method of doing it. And of course, this works for any spin. The higher the spin, you just put more points on the sphere. So this is a nice way of characterizing the ray space of an n-level system. It's an unordered n-tuple of n points on a sphere, right? And of course, you have to think a little bit to make sure that it goes in the reverse direction as well. That you give me any state of the spin-1 system, I can produce those 2 points. Now, what is not obvious and is quite nice, restores one's faith in justice, is that if you give me a Z1, Z2, Z3 of a spin-1 system, and I solve that quadratic equation and get 2 points, those 2 exactly happen to be the 2 where if you construct one spinner corresponding to each point and you symmetrize them, you get back your original Z1, Z2, Z3, right? So that's interesting. The third way is purely geometric, and I don't think Sridhar published it, but it might well be there somewhere. So you take this ellipse. So now you're thinking classical mechanics. In fact, Sridhar works in stellar dynamics, so it's very natural for him to do this. You've got this elliptic orbit. So you have the angular momentum of that orbit. So let's agree that you will always look on this plane from a direction in which things appear to go counterclockwise, okay? So I omitted the arrow on this, but it's there. Then you construct 2 vectors, and these 2 vectors have to do 2 jobs, and they do it very nicely. The component along their bisector gives you the angular momentum in units of the maximum possible value. So for example, if it happens to be a circular orbit, the 2 vectors coalesce with each other. Then the components of these 2 vectors in the plane give you the foci of the ellipse. So all this takes a little bit of calculation, right? And you can see it has the right behavior because when you go to circular orbits, the foci should become meaningless, and that's exactly what happens, right? When these 2 merge, the 2 feet also merge, feet of the perpendiculars merge. Equally, when the thing has no angular momentum, when it's a linearly polarized state, the 2 vectors lie down in this plane, anti-parallel to each other. The ellipse degenerates into its major axis. So anyway, we have 3, and as I said, the marvelous thing, which honestly I did not check till I prepared this lecture, is that all 3 give you the same points on the Poincare sphere, okay? So this is the ray space. But strictly speaking, is the ray space of a 3-level system, right? Is the ray space of, now, Sridhar and I collaborated a bit on this. I'll be putting down the reference later. So John Haney's paper actually works out in a very nice geometric way, in fact. As you move along some path in this space, the path being defined by this pair of points on a sphere, he gave a nice expression for the geometric phase, okay? However, if we go back to the original motivation for this, that motivation was to characterize the set of all polarizations for all directions of propagation. Then you need to do a little more work. And the reason is this. If I just give you an elliptic orbit, it could either be, let's say even a circular orbit, it could either be right circular for something going this way or left circular for going something that way, right? So really, if the space you're interested in is the space of all directions with polarizations sitting on top of each point as fibers, then this space, CP2, one element of CP2 seems to correspond to 2 elements of that space, namely 2 beams going in opposite directions, okay? But that would be easily fixed. You just make 2 copies of CP2, comes free, right? And say one represents, right rotating ellipses, one represents left rotating ellipses. You can do that, but the doubling occurs for all orbits with angular momentum. But if you take the linear polarizations, it gets slightly worse. If you give me a linear polarization, the k vector could be in an entire circle. Right? So this approach, I mean, in principle, if you were a brilliant topologist, you would say, okay, take 2 copies of CP2, attach them at this boundary, which happens to represent all linear polarizations, all right? Which is actually the projective sphere which you saw, and then blow up each point of that into a circle, right? Now that was a bit too difficult for us, so that's not the way to do it, okay? So we just went back. So we're not worrying about the geometric phase right now. We're just asking a purely topological question. You have this set of light beams, with, as I said, going in all directions with all possible polarizations. What's the topology of that space? Okay. We'd have been very happy if it had been twisted, okay? I mean, if the space is not twisted, it's like reading a detective novel at the end and saying the butler did it, you know? So, unfortunately, it was not twisted, okay? And let me tell you why, okay? Incidentally, that does not invalidate the earlier work done on geometric phase for spin 1, okay? Started off by Rajan Bhandari, and I think brought to a very nice form in John Haney's paper. And the reason is that the place where the mapping goes wrong are precisely the places where geometric phase is 0, all these linear polarizations. So you don't worry about it, okay? So now one is not primarily worrying about geometric phases, one is asking where am I? Okay, yeah, I still have some time. So what's the topology of the space, right? Which consists of all beams, all directions on it. So one way to do this would be to suppose, so now you have a sphere of directions, right? Directions of propagation. And the polarization vectors live on the tangent space to this sphere. So let's say at each point, we are able to put 2 basis vectors, complex vectors, right? In general complex vectors, right? Then any polarized beam could be expanded in terms of these 2 complex vectors, and you will get a Z1 and a Z2, and you could manufacture a Poincare sphere. Okay? Now, when will this be a Cartesian product? When you can find this basis at every point, right? In a completely smooth manner, without any obstacles, without things going wrong somewhere. Okay? Now, it's a well-known idea in topology that you cannot do this with linear polarization. So, suppose you just wanted 2 linear polarizations, 2 tangent vectors, right? This is a well-known statement called the hairy ball theorem, which does not allow you to smoothly associate 1 tangent vector, you know, everywhere on this. Or a very popular way of saying it is that if you represented the wind everywhere on Earth, there must be at least a couple of points where the wind vanishes, right? However, we have the luxury of having complex polarization vectors. So we looked at this problem, and in this case, I think we kept exchanging notes. I knew that Professor Mukunda and his collaborators, Subhash Chaturvedi and Simon, I think, were also looking at this problem in very different ways, as you would have realized by now. So I will not take you through the whole story, but I've said. So the way I'm going to manufacture this basis in a completely smooth way for any direction, right? So now this is the basis. You want to expand these oscillators. You want to create a Z1, Z2. So the basis has to be complex, right? I mean, with phase. So you want the phase of these basis vectors to vary continuously. You want of course, the polarization also to vary continuously. So this figure represents, the red one represents a electric charge, and imagine there's a neutralizing electric charge at the center, going round and round in a circle, and it's going to radiate something in all directions with some amplitude and some phase. So let's go to a sphere so that the phase due to the propagation is the same, you know, distance divided by lambda into 2 pi. And then look at how, so right on top you will get, in this particular case, you will get right circular polarization. In the opposite direction, you'll get left circular. On the equator, you will get linear, but of course the phase of that linear will vary. as you go around, right? As you can see from this picture. So that's one basis vector. Now you get the other basis vector slightly deviously by taking a magnetic charge, okay? I mean, this is allowed, okay? Because we're just using it to construct an electromagnetic field far away. And then put an opposite magnetic charge in the center and send it around in the opposite direction. So of course, this will give you opposite circular on the top. And interestingly, on the equator, it'll give you a magnetic field in the equatorial plane, which means the electric field perpendicular to the equatorial plane. So, I mean, by the physical nature of this, it just has to be smooth. The phase has to be smooth, the polarization has to be smooth, okay? So this is the introductory part of this long paper which we wrote. And then once having got a basis, on the one hand, as I said, the butler did it. So, the manifold is S2 cross S2, no twists, nothing. Having done it, we did look at the geometric phase and so on and checked that it agrees with everything else, okay? Mukunda, did you also have some references as the title? No, but there was no prior consultation. I also called it some references. So that's a way of saying that this is not all reference, okay? But it's also by way of acknowledgement, okay? I have acknowledged, some people in that pictorial depiction, but I had the good fortune to have a ringside seat when Samuel and Bandari were working on this. I mean, 88 is when it finally came out, but obviously it was happening before that. Incidentally, the chronology, as I remember it, is that Ramseshan and I wrote this paper in 86, I think. And when Michael visited, I actually wasn't around. But I think Ramseshan and Sam did give him a copy of that paper, and he told you what happened after that, right? So that was a privilege, and of course, discussed the subject any number of times with them. A kind of ringside seat, just a few meters away, and only maybe a kilometer away, or 1.5 kilometers away were Mukunda and Simon. And as I said, if there was any lecture, I usually went there. So I at least heard some of these things, right? But you can see that, I mean, from the way I've presented the subject, that I'm a little more comfortable with this. It's a slightly different way of doing things, maybe not as powerful. Then there is this paper, which if I had been well educated enough, I would not have written, right? This one. But it goes through, it has the Pancharatnam phase convention, but without citing him, and showing that it fails at the orthogonal point, and showing that any phase convention fails, basically. Which, if I had known about the theory of fiber bundles, I would not have written that paper. Extensive review article by Rajan Bhandari. Okay, so this is the one person in this list whom I didn't meet. I have met him, but before he wrote this paper. And, but certainly I drew a lot of inspiration from that paper, including learning about Majorana and thinking geometry. This is the paper that Sridhar and I wrote. And I've had lots of discussions with Sridhar on this. And as I said, by this time, I think I was in Pune, and so it had gone to hundreds of kilometers, or a few hundreds of kilometers, but we still exchanged mails and so on. And this is their attack on this problem of direction plus polarization, which actually Mukunda did not mention in his, I mean, he had a lot of ground to cover, okay? So yes, I'd like to stop here and take any discussion or questions.